Everyone. This is a video on the Gaussian integral, and it's in the Richard Feynman's way. It's actually the method of taking partial derivatives, like a dummy variable. Then you partially derivate the function, then you integrate it by forming a differential equation. Okay, so I'm gonna get started with it. So first, let's see what actually is the Gaussian integral. Well, obviously we know that it is given by this, but this signifies the area of this graph, which looks something like this, and this is the Gaussian probability distribution. So basically there's some types of probability distributions, and one of them is Gaussian probability distribution, and we want to find out the area of this function. Well, in this method, probably the best method to find it. It's pretty simple to understand. So first of all, let's go and take a dummy variable. But first, obviously this is an even function, so I would just break it into two parts, and then I can take some dummy variable, let's say 0 to t e power minus x square. The problem with taking a dummy variable like this, because this is also possible in integrals like e power minus x square sine x square, sorry, uh, in in integrals like this, when you can take I of t to be this, and then when you take the partial derivative, you would have e power minus tx square as it is, and then you would have x square, and this would cancel the x square. This would be helpful, but here it is not, because you don't need to cancel anything out. You would have an extra x square term here, so that won't help. So let's take this term, and yeah, so this is my I of t. I am differentiating it to get to this thing, times e power minus t square using the Newton-Leibniz rule. And obviously, as t is just a constant with respect to x, I can just take this. I mean, it is a function of t, but I is the function of t. With respect to this integral, it is not. Yeah. Okay. So now to make this easier, I want something that I can maybe subtract from here. Divide here, and just like this, the x square terms cancelling out. I want something like that. So I am thinking of, first I wanna find what would give me the partial derivative of this function, and I'm thinking a little. I get this, that del by del t of e power minus t square times u square plus 1 upon u square plus 1, if I had something like that. And also, if I take t to be 0, I would be left with 1 by u square plus 1, which would just give me an integral of tan inverse u. So yeah, this looks like a good way to go. So I take this and I get minus 2t times e power minus t square u square plus 1, and then you get u square plus 1, which just gets cancelled. So yeah, no need. Okay, so I think that's pretty obvious. So you are left with this term. So one second. Yeah, so I want something like this. So for this, what I would do is that I would put x is equal to tu. So this would give me dx is equal to t times du. Remember, t is a constant, so 0 to 1 times t would give t 2, and here you would have e power minus u square, so t square times u square plus 1, and there would be a t, and there would be a du and minus. This is I dash t written in the form of u. Okay, so this is basically the standard form of writing an integral in the Feynman's technique of integration. Now basically I just found out that the partial derivative of this function is this, I mean in the total, this whole thing. Yeah, so I can just say that I dash of t is equal to minus 0 to 1 del by del t of e power minus t square u square plus 1 upon u square plus 1 du, and in this case I can replace del by t, and I would get something like one second, dy dt into 1 e power minus t square u square plus 1 upon, so this should give me I of t to be this function, or as I like to do it, I would, let's take this as happy face of t. Okay, so okay, so when I was taking the value of t, what I decided was that I want to use the values t tending to infinity and t tending to 0. So what if I just choose to use the value of I of t? So clearly from here you can say that I of 0 is equal to 0. So I would put that in here. So happy face of 0 is equal to, this whole term collapses, you are just left with this, right, which we talked about earlier, plus c, and this is 0, so c is basically just pi by 4, right? One second. Yeah, yeah, absolutely fine. Okay, so I know the I of t, or my happy face of t, it's a little bit creepy, yeah, is equal to, so I can write this I of t to be this. Now this is going to be crucial while I'm solving the integral. So now I can just go to the solution. I of t was just the it was the square of 0 to t e power minus x square dx squared, right? So I can put yeah, so I can take the Gaussian integral to be 2 times limit t tending infinity of root of I of t. I think that's pretty obvious, and obviously I don't need to worry about the sign of the root because it's going to be positive. So yeah, so I put this in, this would be limit t tending infinity of I of t. So when you put limit t tending infinity in the function I of t, you shall get this thing cancelling out and you would only be left with pi by 4. So root pi by 4, and this would be root pi, and that is pretty simple. I didn't use any, it wasn't that complex to be honest. Also you can write the error function in this. This would also be a part of the probability distribution, and I think that should be fine. Also if you have e power x square, you can also find this. Obviously it's not from 0 to infinity, you can just take it as let's say, I mean, if I'm taking something like this, because I wanna uh, write it in that form. So so 1 by I mean, that's what happened here, right? From here, sorry. So minus iota times root pi by 2 times error function of u. This should be when you're writing the integral, and when you put limits you shall get the same thing, that root of pi. Sorry. Yeah, so that is it. If I wanna summarize it, well, all I did was I took this function and I took t as my dummy variable, and there's also many ways to solve this using the same Richard Feynman technique, but you can this one just seemed the most relatable or easiest to understand, to be honest. And also I hope you get the reason why I didn't take t here, because yeah, I tried it, I tried to do it that way and it just didn't turn out well. Also you can solve it using polar coordinates, basically by taking x square plus y square to be r square, and dx dy to be r dr d theta, and you can just integrate 0 to infinity, 0 to infinity r square e power minus r square. uh, yeah, I hope I'm doing right. Yeah, r dr d theta 1 by 2 and 2. So something like this could be the Gaussian integral, something like that, and you can solve using polar coordinates as well. Other than that, I just differentiated first, then I used partial derivatives here, and yeah, I think it was pretty easy to understand anyways. So yeah, thanks for watching.